This lecture is going over the independent samples worksheet, the second question on the worksheet. This particular question is about the 1900s with the U.S. Center for Disease Control. And in the 1900s, we only recorded two different ethnicities. You were either white or non-white due to the prevalence in the United States of white individuals as compared to non-white individuals. So, this particular question states the U.S. Center for Disease Control reports that the mean life expectancy was 47.6 years for whites born in 1900 and 33 years for non-whites. Suppose that you randomly survey death records for people born in 1900 for certain countries, in a certain country. Of the 124 white individuals, the mean lifespan was 43.5 years with a standard deviation of 12.7 years. Of the 82 non-white individuals, the mean lifespan was 34.1 years with a standard deviation of 15.6 years. Conduct a hypothesis test to see if the mean lifespan in the countries were the same for whites and non-whites with a 10% chance of committing type 1 error. So first of all, this can be a little confusing because you may be wondering, are we supposed to be comparing the U.S. Center for Disease Control compared to this country? No, this is just background information, and we are actually comparing in the new country white life expectancy compared to non-white life expectancy. Okay, so we're going to go through this. This is just background information. Then we have the independent variable, which is whether or not you're white or non-white. Then we have a sample size of 206 because we have 82 individuals that are non-white. And then we have 124 individuals that are white. And then we've got the standard deviation of, let's see here, new comment, SD of sample 1 and is 12.7, and then we have the mean of sample 1 is 45.3, and then we have the mean of sample 2. Mean of sample 2 is 34.1. And then we also have the standard deviation of sample 2. SD sample 2 is 15.6. And then we have the alpha level of 10% or 0.1. So let's go ahead and go down here. So what is it that I really want to know? What I really want to know is there a difference in the average lifespan between individuals who are white compared to not white in this particular country that we're talking about? So before we do that, we need to determine are we assuming that individuals who are white are going to live longer, individuals who are white are going to live less, and notice that it's in that order, individuals who are white as compared to not white. Is there anything there that says that they anticipate that one is going to live longer than the other? And notice it just says a difference, okay? So right here, conduct a hypothesis test to see if they are the same, or in other words, or if they're different. And so our hypothesis test is specifically going to be exploring, are the two of these different? Are the two of these different? And so our symbol is not going to be the greater than or less than sign, it's going to be the equal sign. So coming down here, we have the mean of individuals who are white for the null hypothesis. For the hypothesis says that there's no difference compared to the mean of individuals who are not white. And we've got the mean of individuals who are white is equal to the mean of the individuals who are not white. Okay. So what this says is there is no difference in the average lifespan between individuals who are white compared to the individuals who are not white. And then right here, the alternative hypothesis, individuals who are white the mean of individuals' lifespan who are white is not equal to individuals who are not white. In other words, there is a difference. There is a difference between the average lifespan between individuals who are white compared to individuals who are not white. So what is it that we're actually looking at? And I've got this fun little piece of information. I'm actually going to move it up. Let's see here. And we're going to just do a few calculations. I'm going to move this up right here. We're looking at a level of significance of 0.1. Level of significance of 0.1, and when we're looking at a level of significance of 0.1, that means that we have a confidence interval, a 90% confidence interval. And so this question that's being asked is saying, hey, if you use a 90% confidence interval, and you compare the two of these distributions, can we determine that the two of these distributions are different? That they are in fact that the mean, the point estimate of the mean for individuals who are white is different than the point estimate of the mean of individuals who are not white. We want to see if they're different. So right here we have the individuals who are white compared to the individuals who are not white. We've got the mean. If you come right up here, the mean of individuals who are white is 45.3 years. So we've got 45.3 right there. And then the mean of individuals who are not white is 34.1 years. And so we've got 34.1 right there. And then I came over here to this fun Excel file, and we're going to do a little bit of math. With this particular distribution, you notice that the confidence intervals are already there, the upper and lower limit of the 90% confidence interval. And in order to find this, what we need to do is find the margin of error. Okay, so I'm going to zoom out here. We've got the margin of error right here. And so the margin of error is the z-score, or in this case, what is the z-score? Well, we're about to find it right down here, but I'm going to tell you that the z-score is 1.645 because it's a two-tailed test, so it's plus or minus 1.645. And then for the margin of error, we've got the standard deviation divided by the square root of n. So what's the standard deviation for each one of these? We've got 12.7, and then we also have 15.6. So we've got, for this formula, the standard deviation divided by the square root of n. What's the sample size? The sample sizes are 124 are in this sample, and 82 are in this sample. So we've got 124 and 82. So we've got the sample size. And so for this, what we're going to do now is take the z-score, which is equals 1.645, and multiply it by the standard deviation divided by the square root of n. Okay, and I'm going to put these in parentheses. Or the square root of the number of observations, which gives us a margin of error of 1.876 for individuals who are white. So we're going to put margin of error, and then we're going to do the same formula here. So equals the z-score multiplied by the standard deviation divided by the square root of the number in the observations. So that gives us the margin of error for individuals who are not white. So white, not white. And then in order to be able to find this, find the upper and lower limit, we just take the mean, Control C, So this is these are the means, and then we take equals 45 minus the margin of error, and then equals 45.3 plus the margin of error. And then we take 34.1 equals 34.1 minus the margin of error, and then equals 34.1 plus the margin of error, which gives us the lower limit, the mean, and the upper limit. Okay, so we've got the lower limit, let's go right there, mean and upper limit. And so this is basically the distribution of, or this is giving us a good picture of these two distributions. So we've got the individuals who are white over here on the right-hand side, the individuals who are not white over here on the left-hand side, and we've got their confidence intervals of their point estimates of the mean. And so we've got the average individual who's not white. This is the best point estimate of the mean that we have, the best estimate that we have. And we want to know, when we have our best estimate of this mean and we are 90% confident that it's between this threshold, how does it compare to our best estimate of the mean over here and our confidence interval of this point estimate of 90%? If the two of these confidence intervals, if they overlap, okay, if they overlap like this, then we're going to have to say we cannot conclude that they are different. Okay, that's not accepting that they're the same. We're just saying we can't conclude that they're different. Okay, and then if they are apart like this, basically we're saying we are 90% confident that these are different. Except we're actually a lot more confident than that because there's a p-value. And so we're basically 99.99% confident that they're different. So we've got this distribution over here, and notice that this distribution is spread out a little bit wider, and this distribution is a little bit more ellipticardic. This is more platycardic, and we don't have the skewness. I didn't calculate the skewness here, but we have one distribution that's a little bit wider spread out and one that's a little bit narrower. So we've got the margin of error and the standard errors, so on and so forth. So that is what we're actually looking at. So that brings us to the test statistic. What is the test statistic? Or a 0.1 probability of type 1 error. Then what is the test statistic? You can use a t-test statistic. Notice that it only gives you the sample standard deviation and the sample standard deviations, but because this is an independent sample, we actually have over 200 observations. More specifically, we have 206 observations, and because we have 206 observations, running a t-test would be pretty much the exact same thing as running a t-test. A t would be the same as a z in this particular situation. So because of that, we might as well just run a z because it's just a little bit more easy to interpret and communicate. So we run a z-test. So the z, two-tailed, and alpha allow us to calculate the z critical value. And in order to calculate the z critical value, we can just go to the chart, which I can pull up I'm going to pull up the PDF chart. And so I've got the critical values diagram right here. So this is a really great resource for you. And is this a two-tailed test, an upper-tailed test, or is this a lower-tailed test? This is a two-tailed test, right? Is there a difference? This is a two-tailed test with an alpha of 0.1. Two-tailed test, alpha of 0.1. So therefore, the critical value is plus or minus 1.645. So if it was a one-tail upper, then the 0.1 would be 1.282, and if it was a lower, it would be negative 1.282, but it's not an upper or a lower. It is a two-tailed test for 1.645 plus or minus. Okay, so we've got plus or minus 1.645, and now we are going to calculate the z value. Okay, and I've already actually got the calculations right here, and this is the z, this is how to calculate a z statistic for an independent samples t-test. We have the mean of the first sample minus the mean of the second sample divided by the square root of this variance over the number of observations and the variance over the number of observations for each sample, and you take the square root of that. And so I've actually already done that over here. So I've got the difference. So this right here, 11.2, I took the mean of the first minus the mean of the second to give me the difference of 11.2 years. And then after that, I have 12.7, which is the standard deviation squared over the sample size of 124, plus 15.6 squared divided by 82, which gives us 4.2685 dot 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 dot. So now what I need to do is take the square root of that. So I take the square root of the equation that I just put in there, and that gives me 2.066. This right here is otherwise known as the pooled standard deviation. Okay, the pooled standard deviation, and if I square it right here, this right here is the pooled variance. And this is the difference between the two samples. Okay, so we've got the variance, the standard deviation, so on and so forth, and then in order to get z-calc, what we need to do is we need to take the difference and divide the difference by the pooled standard deviation, which gives us z-calc, and z-calc is 5.42. 5.42. Next, what is our decision rule? The decision rule is reject the null hypothesis if z-calc is less than negative 1.645 or if z-calc is greater than 1.645. Fail to reject the null hypothesis if the null fail to reject the null hypothesis if z-calc is between negative 1.645 and 1.645. So what does that look like down here? And yours is all spread out, but I put it together just to make the video shorter. So make sure that you move this up, and so we've got the z critical value of negative 1.645, and then we've got the other z critical value of positive 1.645, because this is a two-tailed test. So if you have a calculated value that is at the green level or beyond the green level, so anywhere in this green area, if you have a z calculated value that's anywhere in this green area, then you're going to be able to reject the null hypothesis. If you have a z calculated value that's in the middle in here, you're going to have to fail to reject the null hypothesis. Fail to reject the null hypothesis. But we have a z calculated value right here of 5.421, and so because the z calculated value of 5.421 is beyond the z critical value of 1.645, then we know that we are going to reject the null hypothesis because this z calculated value is on the outside. It's not on the inside. If it was in here, we would fail to reject, but because it's out here, we are able to reject the null hypothesis. So, and this is supposed to be up here. And so we just went over this, but we are going to look at the critical value and the calculated value and compare the two. So we have the critical value, we have the calculated value, and so just copy it from up above and place it right there. And then what is the p-value? So there's a couple ways to get this p-value. You can pull out the chart, the z chart, but you're not going to be able to find the p-value with the z chart. Okay, so what I'm going to suggest you do is come over to Excel. And when you come over to Excel, there's this really wonderful formula, and I'm going to make this a little bit bigger. This formula right here, norm.s.dist. Okay, so I'm going to show you what this does. Equals norm.s.dist. And then we need to put the z value. And remember, we calculated the z value earlier right up here. where is the z-value? Right here. So we've got the z-value. Okay. And then after that, we need to put in whether or not we want a cumulative or if we want the probability density function. So I'm going to put false and for the probability density function, and this is going to tell me that the probability of getting this particular result is 1.6579 raised to the negative 7th. So in other words, put 7 zeros in front of that, and that's what you've got. So the probability of this occurring is very low. And I hope that you take the time to practice this, the norm.s.dist. This formula comes in handy quite a bit, especially when you're on your quizzes and exams. If I ask you, hey, what's the calculated value, and I give you, or sorry, if I ask you for the probability of a particular calculated value, and then you have the ability to do that. There's also, if you go to the Excel formulas, you can do the same thing with the t and the chi-squared, and it'll give you the critical values, and then the t and the norm function give you the p-values. So the probability. So the probability of this result is 1.6579 raised to the negative 7th. So what is it that we can conclude? Since the p-value is less than the alpha, it is statistically significant. And I don't know why this is in here. Let's get rid of that. So this is statistically significant. That's what I want to know. Is it statistically significant? Yes. Okay. So next, what is your decision? Control I. We reject the null hypothesis as the z-calc value of 5.421 is more extreme than the z-critical value of 1.645. Okay, so moving on. Interpret your results. The life expectancy difference. This is the first thing I'm telling you. Hey, there is a difference. The difference of 11.2 years is too large to have occurred randomly by chance. The probability of this occurring randomly is less than 0.01%. The life expectancy of individuals who are white in this country, the country that we're referring to, is longer than individuals who are not white. So that is how you would write this up. Go through the 6-step process. And take the time to, put these charts in. You don't have to do this chart right here, and I should have stopped and said that you didn't have to do that chart. This chart is just for you to see how this works. And then hopefully the z-calc, take a look at the calculations, and they will help you to be able to calculate the z-value.